Good evening, everyone. So today we welcome to my YouTube channel, Avatarm. So today we are going to see this lecture on uniform convergence. So we are going to introduce new concept. Let's start today's lecture. What is that new concept? So definition. Let Fn be a sequence of functions. Sequence of functions. Okay. Sequence of functions. Then this sequence is said to be uniformly Cauchy on I if given epsilon greater than 0, there exists capital N belongs to N such that Fn x minus Fm x less than epsilon for all N and M greater than equal to N and X belongs to I. Okay. N comma M greater than equal to capital N and X belongs to I. Okay. So we will prove a result. So you observe one thing. Observation. Suppose my N is N is greater than equal to M. Okay. Then what will happen? Then sorry. Observation. So suppose N is greater than M. Okay. Then what I will do? Then I can write. Then N can be written in this form, M plus P, for some P belongs to natural number. Okay. So we can reduce this definition. So let's say it equation number. We can write 1 in a following way. So I can write it M plus P x minus F M x less than epsilon for all M greater than equal to M and N M greater than equal to N. P belongs to natural number and x belongs to I. Okay, it means p is greater than equal to 1. Okay, because p belongs to natural numbers. Okay. Oh, okay. So if I similarly, I can in a more general way, what can I do? I can do, because n can be greater than equal to n can be equal to m as well. So in this case, it will be, both will be p. P will be a number which can be 0 also. For some p belongs to natural number union 0. It can be 0 also. Okay. It can be 0 also. So write in a proper way. Okay. Comma x belongs to I. Okay. Now we are going to prove one result. Let fn, each fn is from I to R, be a sequence of functions. Okay. Then fn converges uniformly on I if and only if this sequence fn is uniformly Cauchy on I. Okay. So this theorem is called, what is the name of this theorem? This theorem is called Cauchy criterion for uniform convergence. The name of this theorem is Cauchy criterion for uniform convergence. This is the name. Just underline it. So this theorem is called Cauchy criterion for uniform convergence. So let's prove it. Okay. Proof. First assume that fn converges uniformly on I. So this implies there exists some function fi to R such that for any epsilon greater than 0, there exists capital N belongs to N such that such that, or you can write with the property or with fn x minus fx less than epsilon by 2 for all n greater than equal to capital N and x belongs to I. Okay. So now take n and m greater than equal to capital N. Then what we have? We have two inequality fn x minus fx less than epsilon by 2 and fm x minus fx less than epsilon by 2. So combine, so we have, what we have, we will combine these two equations, fn x minus fm x. So these two equations holds for all x belongs to I. Okay. So I can add fx and subtract as well. Fn x minus fx plus fx minus fm x. So this is less than epsilon and this is less than epsilon. So what we got? Epsilon by 2 plus epsilon by 2. That is epsilon. Okay. So we got, what we got? F1 x minus fm x less than epsilon for all n and m greater than equal to capital N, x belongs to I. This implies Fn is uniformly Cauchy on I. So one direction is proved. So assume conversely. Conversely, assume that Fn is uniformly Cauchy on I. Okay. So what does it mean? Okay. Then given any epsilon greater than 0, we have n belongs to n such that fn x minus fm x less than epsilon by 2 for all n and m greater than equal to n and x belongs to I. Okay. Fix n greater than equal to n and x belongs to I and letting so sorry So let's say equation number 2. So fix x belongs to I. Then we have fn x minus fm x less than epsilon by 2. Okay. For all n and m greater than equal to 1. So this implies fn x is Cauchy in R, and Cauchy sequence is always convergent. So this implies fn converging to some point that is I'm calling fx. Okay, for each x belongs to I. Okay, so now fix n greater than equal to n and x belongs to I, letting m tending to infinity in 2, equation number 2. We get fn x minus this limit. When you will m tending to infinity, it will go to fx. So it will be fx. And this inequality can be equal as well for all n greater than equal to n and x belongs to R. But this is strictly less than epsilon. So this implies what does it mean? Fn converges to F uniformly on I. So this implies Fn converges uniformly on I. So this theorem is proved. Okay. So we are going to see another definition. What is series of sequence of function? Let Fn be a sequence of functions Fn I to R for each n belongs to n. Okay. Then consider this series and it goes 1 to infinity Fn x. So this is called series of functions corresponding to base functions. Okay. Okay. Now how can I will say that this series converges uniformly? This series converges uniformly on I if Sm is equal to summation n goes to 1 to m Fnx converges uniformly. You take partial sum. This series will converge. We say that this series converges uniformly on I. Means what? We are taking partial sum. If partial sum converges uniformly on I, we will say that this series converges uniformly on I. Okay. So, so we are going to study M-test. Weierstrass M-test. Sorry. Weierstrass M-test. What is that? Let be Fn. Fnx be a series of functions on I. Okay. If there exists a a convergent series Mn of positive terms, sorry, non-negative terms, non-negative terms. Non-negative terms means what? Each Mn will be greater than or equal to 0. What does it mean? Term is non-negative. It means each Mn is greater than or equal to 0. Okay. Then this series of functions converges uniformly and absolutely on I. Let's see its proof. How to prove this? Proof. Now take this partial sum. We have taken this partial sum. Okay. Now what is So what is this? S M plus P minus SM. What will be this? So this will be equal to F M plus P X plus M plus P minus 1 X S M plus 1 X. So the one thing is, if there exists a series of non-negative terms with Fn X is less than Mn, okay, for all n belongs to n and x belongs to I, then series converges uniformly and absolutely on I. Okay, this condition is required. Okay, so we have defined partial sum. If we can show that partial sum is a uniformly Cauchy, then series will be uniformly convergent, because partial sum will be uniformly convergent. So if we can show that partial sum is uniformly Cauchy, so it means partial sum is uniformly convergent. It means series is uniformly convergent. Okay. Now what about this bitriangle inequality? Okay. What is this? This is M n plus P M M plus P minus 1. Okay. Plus M1. So what is this? This is this is equal to summation and goes to 1 to M plus P Mn minus and goes 1 to M Mn. So let's say it's equation number 3. So now let this series. So I'm saying M Sm dash is equal to summation and goes to 1 to M Mn. But this series is convergent. So what does it mean? Given epsilon greater than 0, there exists capital N belongs to N such that Sm dash minus Sm plus P dash is less than, to write here this, is less than epsilon for all m greater than equal to n and P belongs to n. Okay. So I am writing, so in equation number, uh, so this is x here, this is x here, this is x here. So this equation is true for all x belongs to I. Okay. Okay. Now let's take equation number 4. From 3 and 4, we have Sm plus P x minus Sm x less than epsilon for all m greater than equal to n. P belongs to natural number union 0 and x belongs to I. So what is the meaning of this? This implies this sequence Sn is uniformly Cauchy on I. Okay. So this is meaning. What is the meaning of this? Uniformly Cauchy means is uniformly convergent on I. Now partial sum is uniformly convergent. So series is uniformly convergent. So this implies converges uniformly on I. Okay, so we have proved this result. Now we are going to see some examples on this. So what are those examples? Examples. So see, first example. Okay, example first is if summation n goes to 1 to infinity a n be convergent series of non-negative terms okay, then so that the series summation n goes to 1 to infinity a n x to the power n 1 plus x to the power 2n and n goes to 1 to infinity. An x to the power 2n upon 1 plus x to the power 2n converges uniformly on R. So how to prove it? You see this series an x to the power n 1 plus x to the power 2n. Okay, x to the power 2n. So what is my so this is my fnx. So this is my fnx. So fnx is an x to the power n 1 plus x2 to the power n x to the power 2n. Okay. So now fnx, what is this? An, this is non-negative. Okay. So x, okay, and 1 plus x to the power 2n. Now, if you note that, I can write this. So this is, I can also write this value 2n. This never exceed 1 by 2. So it means this is less than an by 2. So what is my mn? Mn is this, an by 2. So let mn is equal to an by 2. So we have fnx less than mn. Now, if this series, note this series summation n goes to 1 to infinity, mn, what is that? That is 1 by 2 will come out. And it is given that this series converges. So main series converges. Okay. So it is already given in question that this series converges. So it means converges. And each mn is nothing but an by 2. An are non-negative, so they are also non-negative. So by Weierstrass M-test, the series an x to the power n 1 plus x to the power 2n converges uniformly on R. Okay. Now another thing you see that another question. This question, second part of this question. First you note that this is my Fn. So Fn is this. So Fn x an. So this is non-negative. Okay. So nothing will happen. It will remain as it is. So we know that, so x 2 to the power n, 1 plus x to the, this is non-negative. So this is less than equal to 1. Because numerator is, this is non-negative, this is non-negative, and denominator is greater than numerator. So it will be less than equal to 1. So what we got? Let's say it mn. So that mn is equal to an. So fn x is less than mn. And each mn term is greater than an, and that is greater than. And also this series is nothing but, and this series converges. Means mn series is converges. So this implies by Weierstrass M-test that the series an x to the power 2n 1 plus x to the power 2n converges uniformly on R. Okay. Now see second example. So both the series in example 1 converges uniformly. Okay. Now what about this? So let R in this range. Thus the series R to the power n sine and theta converge on R, converge on R. Here theta, here this is function of theta, okay, and theta belongs to R. Whether this series converges, you see that this series converge uniformly on R. So you see that if I take my mn is equal to R to the power n, and R is in this range, so this becomes geometric series, and geometric series converges if your common ratio R is less than 1. In its absolute value is less than 1. So this series converges. And its term is non-negative because R is in this range. So R to the power n will be non-negative, positive. Okay. And you see that Fn, what is my Fn? Theta. Fn theta is R to the power n sine n theta. So what is Fn theta? Sine theta value is always less than equal to 1. Okay. That is Mn. So by Weierstrass M-test, by Weierstrass M-test, the series and theta converges uniformly on R. It means theta belonging to R. Okay. So today we have seen what is uniformly Cauchy sequence of functions. Okay. And we have proved that a sequence is uniformly convergent if and only if it is uniformly Cauchy. Okay. By using that, we have studied the uniform convergence of series, and we have also proved a result to show uniform convergence for a series of functions, that is Weierstrass M-test. We have done few examples on that, okay. So today's lecture up to this. We will see you in next class. Kindly like, share, comment and subscribe my YouTube channel. Thank you very much for today's lecture. Thank you very much. We will see you in next class.